Okay, so this question is asking why CH3 COCH2F is more acidic than CH3 COCH3, right? So the first thing we have to do is draw out this in bond line form. So CH3 is just a methyl group like that. COCH2F. What do you think CO is going to be in this bond line form here? Like, what is the functional group of CO from this condensed formula?
CO is alkene. No, not alkene, carbonyl.
Carbonyl, right? Um, like that, where that's the CO right there, and then CH2 F, like that. That's the structure. CH3 CO CH2 F. CH3 CO CH3 is this here, this acetone here. Right. Now the hydrogen that they are going to refer to is that alpha hydrogen here compared to this alpha hydrogen here. Right. So the very first thing to do when you're determining the strength of acid is draw out the conjugate base. So let's say some base comes in, grabs that alpha hydrogen right there, deprotonates it, and gives that alpha carbon a negative charge. That's going to give us this conjugate base here and this conjugate base right here. Which one is more stable and why? Which negative charge is more stable and why?
The left one, because there's a fluorine atom, so fluorine has a lot of electron negativity.
Uh-huh. Right. Electron negativity. And another way to say that is that this is an electron withdrawing group. Right? Which would withdraw electrons from that negative charge, making it more delocalized, more stable than this localized negative charge here. So the answer of why this is more acidic than this is because of this electron withdrawing group here. Right? So let's put that as the answer. Okay. What signal will the protons of the methyl group of the following compound produce on that 1H NMR spectrum? Right. So this is asking for how many unique peaks would this methyl group have on the H NMR? So let's say we have that Br, 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 right? The ones on the methyl group are these three hydrogens here. How many neighbors do these two hydrogens have right here?
0.
Yeah, 0 neighbors. So when we do the n+1 rule, n is going to be 0. 0 plus 1 is 1. So this is going to be a singlet, right? It's not going to be no signal because it will have one signal from the n+1 rule, right? N+1 is the number of peaks, right? Sub-peaks. Yeah, next. Okay, so this is asking for which of the following compounds is optically inactive. What does it mean for something to be optically active?
Unstable.
So for something to be optically active, another way of saying that is that it has to be chiral.
Oh.
Chiral. And for it to be chiral, it needs to have at least one chiral center and no plane of symmetry. right? So all of these answer choices here do have chiral centers, right? So we cannot look at this factor. We have to look at this factor here. They're asking for optically inactive, right? So if we're looking for optically inactive molecule, we have to look for a molecule that has a planar symmetry, because if it has a planar symmetry, then it would be optically inactive. Which one of these Fisher projections has a planar symmetry?
This one.
Yeah, that one. That's the one that is going to be optically inactive. Because we have a plane of symmetry down that middle right there. This is optically inactive. Which compound would produce a large peak at approximately 1710 on the IR spectrum? So what functional group shows up at around 1700 on the IR?
Carbonyl.
Carbonyl, yeah. So you just have to figure out which molecule of those answer choices has a carbonyl attached to it, which is ethanal. Yeah, ethanal, which has an aldehyde. Which, okay, H&MR spectrum. So let's get rid of answer choices first. For A, we have an alcohol, right? But what does an alcohol show up as on the HNMR? Like what kind of peak? Is it going to be sharp or is it going to be broad?
Broad.
Broad peak, right? But we do not have any broad peak here, so get rid of A.
Wait, what does a broad peak look like?
Yeah, it would look like that, right, on the HNMR.
Also, there's 1, 2, 3 different types of hydrogens. So 1, 2, 3.
Yeah, 3 different
One,
unique hydrogens.
This one has 2 because it's
Mhm.
symmetrical. 1, 2, 3. Okay, this one has 3. 1, 2, 3, 4.
Mhm.
Wait, no. Are these the equivalent, like this one and this one?
Yeah, those are equivalent.
So, okay, so 1, 2, 3.
Mhm.
So,
Right. And notice the singlet peak on the HNMR. What does that mean if that peak has a singlet, like singlet subpeak? How many neighbors does it have?
0.
0, right? So it's most likely going to be that one. Why won't it
This
be
one.
E? Like why won't it be the 3 hydrogens on the right methyl, like the CH3 right there? Yeah, why wouldn't it be that? There's 2 reasons I can see here. Or actually 3 reasons.
I don't know.
So that one next to the oxygen is very electronegative, so it should be de-shielded. That should be around 3 to 4, the singlet peak, but it's at around 2 ppm, so it's not as de-shielded.
Wait, so de-shielded means to the left?
Yeah, to the left.
Okay.
Shielded means to the right. And also, you notice how there's one hydrogen with 6 neighbors. That one hydrogen should have 7 subpeaks, but on the HNMY, we don't have any peak with 7 subpeaks. And also, the 6 hydrogens that are identical, they should only have 1 neighbor, which is a doublet. And we don't have 6 hydrogens with a doublet, so it's not E. Yeah. Next. Which functional group will the product of the reaction contain? So we have CH3COO HCH3OH H2SO4. Okay, so CH3COOH is this carboxylic acid here reacting with methanol and acid catalyst there. Do you know what reaction this would do when we have a carboxylic acid catalyst, and an alcohol?
Wait, so let's do the mechanism and then maybe I'll know.
Yeah. So what's the very first step of the mechanism here when we have a very strong acid? Like, what's the most basic
Protonate the
atom?
OH.
Right. So this is an option, and that's another option. This carbonyl oxygen here is actually more basic than the OH. Right. The reason why is because when we protonate the carbonyl oxygen, this is the conjugate acid we get right here. Right. We notice that this conjugate acid can do resonance like that by making a double bond there and popping that double bond onto that oxygen to create this resonance set right here. But when we protonate the OH, like you said earlier, this is what we get right here. There's no resonance structures that can happen here, right? This pair of electrons cannot go down to make a triple bond there and do that, right? That's not going to happen. But this can happen. This resonance structure can happen there, making this carbonyl oxygen here more basic than the alcohol oxygen right there.
Wait, can't you move that like carbonyl double bond to, yeah,
Oh, like this? Move this carbonyl double bond like down here.
yeah.
Right. Let's see. When that happens, we are going to get this O minus, and then this O H 2 plus. This is very unstable. Right. The 2 plus charge and the negative charge, like this, that's too unstable to exist. Like this would not happen. It can't exist because of the +2 charge and the minus charge right there.
Wait, hold on. Where did the other plus charge come from?
This plus charge right here.
Yeah, so that one was when you protonate it,
Yeah.
but where did the 2 plus come from?
Oh, the 2 plus came from when we moved this double bond down here, right? Because when we calculate formal charge, this oxygen right here has 3 bonds and 1 lone pair of electrons. So it has 1, 2, 3, 4, 5 electrons to itself. 6 minus 5 is +1. Right here, this oxygen has 1, 2, 3, 4, 5. 1, 2, 3. Oh, okay. So there's another reason why this would not occur. This oxygen here breaks the octet rule. So this oxygen here has 2, 4, 6,
Oh,
8,
10.
10 electrons, right? Which breaks the octet rule. Yeah, so that would not happen. Yeah. Okay. So what will get protonated is the carbonyl oxygen, not the alcohol oxygen. Once we protonated the carbonyl oxygen of the carboxylic acid, this carbonyl carbon is now activated and more electrophilic. What can attack that activated electrophile here?
Wait, say that one more time.
Yeah, so when we activated this carbonyl here, this weak electrophile became a strong electrophile with a bigger partial positive charge after we activated it. So now this is a strong electrophile. What do you think can attack that strong electrophile right there?
The alcohol?
Yeah, the alcohol. The CH3OH can then attack that carbonyl carbon and pop the double bond to the oxygen right there. Before, this alcohol cannot attack that carbonyl right there because that carbonyl was too weak. That was a weak electrophile. Once we activated it to a strong electrophile, the alcohol can now attack that strong electrophile to get this tetrahedral intermediate right here.
How did it become a stronger partial positive?
Yeah, it became a stronger partial positive because you know how we made that oxygen a positive charge? That oxygen
Yes.
with a positive charge wants to be stable again, so it wants to
Oh,
withdraw
yeah.
electrons more, making that carbon more positive. Like this oxygen is like more unstable, more reactive, more electron withdrawing. Right? This oxygen here that attacked that carbon is this oxygen right there. And this is the new bond between the oxygen and carbon right there. Right? This oxygen is attached to CH3, a hydrogen, and it still has one lone pair of electrons. Oxygen with 3 bonds and 1 lone pair is a positive charge. Right? Now, what would happen next once we have this tetrahedral intermediate here? This is going to be where we do the proton transfer step. Deprotonate the group that we want to keep, protonate the group that we want to kick out.
Deprotonate the group, so deprotonate. Do we deprotonate the O with the plus?
Yeah, we deprotonate this group because that's the new group that we just added. So we want to keep that group right there. Right. That would make this oxygen neutral, no more plus charge, because it gained a pair of electrons from that bond between the oxygen and hydrogen right there, once we deprotonated that. Right. Now, we want this OH group to leave, but right now it's a bad leaving group. To make that into a good leaving group, we have to protonate it using the acid here and making that oxygen a positive charge, which is a good leaving group. Now, once we have this good leaving group right here, to drive that good leaving group off, we're going to reform the carbonyl and then kick that good leaving group off like that. Once that happens, we get this carbonyl back with its hydrogen still attached and a positive charge, OCH3, where the final step of the mechanism is to neutralize that carbonyl oxygen by deprotonating it.
And why do you use the OH lone pair instead of the methoxy?
OH lone pair, oh, right here?
Yeah.
Yeah, so we want to use the OH lone pair instead of the methoxy because if we use the methoxy instead and take that leaving group out, this is what we're going to get right here. Right? Can we neutralize this positive charge oxygen? Can we deprotonate that?
No.
No, right. So this is going to be like so unstable. It's going to go backwards here, and then it's going to go towards the more stable products here, right? This can happen where we can like reform that carbonyl, kick that out to get this structure here, but this is minor, like it's very minor. It's going to go backwards and then go to the more major form here. Right? Where this is the major product here, which is what functional group here? What is this functional group that we just created?
Ester.
Ester, right. So we created an ester from a carboxylic acid with an alcohol and acidic conditions. This reaction name is Fischer esterification.
Wait, so it's Fischer is with a carboxylic acid and an alcohol?
Yeah, carboxylic acid plus alcohol and some acid catalyst, acid cat, like H2SO4, H3O plus, that would create an ester. Right? It cannot happen in basic conditions. And why cannot work with basic conditions? Fischer esterification.
It's gonna deprotonate the carboxylic acid.
Yeah. Basic conditions is going to deprotonate the carboxylic acid and create a carboxylate, and you end there. Right? That's why it can't happen in basic conditions. This Fischer esterification can only happen in acidic conditions.
Oh, okay.
What was the question? The question was, oh, okay. So what is the name of the following compound? Okay, how would you name this compound here?
Since there's an aldehyde, so it ends with Al.
Al, right?
And the longest carbon chain is 1, 2, 3, 4. So it's butanal.
Butanal.
And then there's a on the second carbon, there's a methyl. So it's 2 methyl butanol.
Right. And we number it from right to left because aldehyde is our highest priority group, where we want the lowest number to be on the highest priority group. We don't number it from left to right. We don't number it 1, 2, 3, 4 because the highest priority group is like way too far away. So that's right. It should be 2-methyl butanol. Yeah, that's it. Which radical is most stable? We went over this kind of question yesterday. Right. Let me just draw out the answer choices. This one, this one, this one, this one, and this one here. Okay, so the first thing I would do is identify each radical. What kind of radical is this? Is it methyl, primary, secondary, tertiary, secondary allylic, tertiary allylic?
Secondary.
Yeah, secondary. How about this one?
Tertiary.
Tertiary. How about this one?
Primary.
Primary. This one?
Secondary allylic.
Yep, secondary allylic. And this one would just be
Vanillic.
yeah, primary vanillic. Which one of these can do resonance? Resonance will triumph everything.
Secondary allylic.
Yeah, so this would be the most stable one because that radical can do resonance to form this resonance structure here. And when it can do resonance structures, it's more delocalized, making it more stable. Oh, yeah, I think we went over the same question yesterday too. The E2 one with the thing, but we could go over that again. So this is CH3, CH2, CH2, CHBr, CH3, reacting with CH3, 3COK, CH3, 3COH. Okay. First, let's draw out this condensed formula into bond line formula. So how would you draw this condensed formula into bond line formula here?
Draw a linear 4 chain of carbon.
Uh-huh.
And then add a bromine.
Uh-huh.
And then add a methyl on the other side of the bromine.
Yeah. And this, what does this look like in bond line form, this reagent here?
Wait, 1, 2, 3. Wait, I think I need workshop on how to draw out the left one, the reagent.
Oh, this one here?
No, I mean the starting material.
Oh, draw this one. Wait, CH3, CH2, CH2, CHBr. Yeah, this is right. You got it.
No, I was thinking of doing just a linear, not branched.
Linear, like like this?
No.
What?
Okay, so like the 4 linear carbons, and then there's going to be a bromine going down. So where that methyl is, you add a bromine, and then you add a methyl the other way.
Oh, this way, like that?
Yeah.
Oh, yeah. This is not good because what would be the charge of that bromine right there? With 2 bonds.
2.
2 bonds and 2 pairs of electrons.
2, 4, 1, 2, 3, 4, 5, 6. Plus 1.
Yeah, plus 1. Right? And if you have it like this, we have 1, 2, 3, 4, 5, 6 carbons. But in the condensed formula, we only have 1, 2, 3, 4, 5 carbons. This is way too
Yeah,
many
so
carbons.
like erase one of the left ones.
This one? Oh, or this one?
Yeah.
Oh, this one. Okay.
I was thinking that.
Oh, this. 1, 2, 3, 4, 5. Let's see the number of hydrogens. 1, 3, 5, 7, 8, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. that's too many hydrogens. Right? This structure has 12 hydrogens, but we only have 11 hydrogens here. So that's another way you could think about it.
Because I
Right?
wasn't paying attention to the carbon on the left side of the bromine. I thought
Oh,
it was
this one here.
CH2, yeah.
Yeah, you thought that was CH2. Yeah, this is a CH, which is that
Yeah.
CH right there. Right? There's no CH here.
Mm-hmm.
And what is that? Oh yeah. Uh-huh. Uh-huh. So what would this reagent look like here?
Wait, what is COK? Tert, no, yeah,
Mhm.
tert, yeah, tert something.
Tert butoxide. Right. Now, once we have this, what is the substrate here attached to the good leaving group here?
Secondary?
Yeah, secondary. And what kind of reagent is this here? Is it a strong base or weak base? Strong base, weak base?
Strong,
Strong base, strong nucleophile. Is it unhindered or hindered?
hindered,
Hindered. So do we go for the Zaitsev product or the Hoffman product?
Hoffman,
Hoffman, right? So how would you predict the product here? Like if we're doing the mechanism, how would we draw the mechanism out? What do we have to draw out here? What do we have to look out for when we try to do this this E2 Hoffman mechanism?
um, steric hindrance,
Yeah, this is sterically hindered, meaning that what carbon are we looking at to deprotonate? The alpha carbon, beta carbon, gamma carbon, delta,
alpha.
epsilon. Alpha. This is the
Oh,
alpha carbon right
okay,
there. That's
then beta,
yeah, beta, the beta carbons. But we have two beta carbons. This beta carbon and that beta carbon right there. Which beta carbon do you want to deprotonate if we have a hindered base here?
the right one.
Yeah, the right one, because that's less sterically hindered, more space for this bulky base to come in, grab, make a double bond, kick out that leaving group to create your Hoffman products here, your less stable double bond right there. Because this hydrogen right here, even though it would give you the more stable double bond, this bulky base here cannot reach it. Cannot reach it because this is too bulky, too much steric hindrance there.
Wait, I forgot. So S1 and E1 go together, but why does E2 and S2 like why are they separate?
Yeah, so E2 here requires a strong base, a strong nucleophile, whereas SN2 requires a weak base, strong nucleophile. And that's like CN minus, N3 minus, something like that, right? Whereas SN1 and E1, they require a weak base, weak nucleophile, which is either going to be neutral water or neutral alcohol, ROH, right? And then a strong base, strong nucleophile would be ROK or RONA, same thing, or RNHNA or RNHK. Right? The K and Na here would make the oxygen negative charge because the K or Na is always positively charged. Because SN1 and E1 require the same reagent, they go together. But SN1 is more major unless heat is added. What the heck, there's a time? Wait, did we get the questions that we worked on correctly though?
Yes.
Oh, okay, that's good, that's good. Let's keep working through this, or unless you have any other problems.
No.
Okay, let's keep working through this. Yes, so we got the right answer for this one here, which is this one.
Okay.
Okay. Okay, let's go over this one here. Okay. So they're asking for which one of the following functional groups will be formed when this reaction happens here. Right. Where this is cyclizing a sugar, linear sugar, into a cyclic sugar. Do you remember the name of this carbonyl carbon right here that's getting attacked for sugar chemistry? Like there's a specific name for that carbon right there. It starts with an A.
Anomeric.
Yeah, anomeric carbon. And whenever we close sugars, right, I'm gonna say that that anomeric carbon is my number 1 carbon, and I'm gonna go down until the attacking atom. 1, 2, 3, 4, 5. And this is not gonna be my number 6 atom because that's not the atom attacking the anomeric carbon. This is my number 6 atom right here, the oxygen that's attacking the anomeric carbon, right? But let's just cyclize this to show you what is formed. I want my numbering system to go straight down, but right now it's not going straight down because it's shifting to the right at the end here. So we have to rotate these 3 groups here, the alcohol, the CH2OH, and the H right there. To make the OH go down, I'm going to rotate it this way here, shifting the CH2OH that way, the H that way. Okay, going clockwise, which would give me this rotated structure here. Right. Where this anomeric carbon is 1, this is 2, this is 3, this is 4. All right, 1, 2, 3, 4, 5, 6. Now the numbering system is going straight down. 1, 2, 3, 4, 5, 6. Right? And imagine that vertical line right there is my arm, and I'm gonna rotate it to the right 90 degrees, which is going to look like this right here with the aldehyde like that. And that's 1, 2, 3, 4. And when I do that, right, let's look at the alcohol on number 2. This is 1, 2, 3, 4, 5, 6. At carbon number 2, is the alcohol going to go up or down when I rotate my arm or this vertical line 90 degrees to the right, clockwise, right? Is it going to go up or down? Up, right. So everything on the left side is going to go up. Everything on the right side is going to go down. You don't have to do this whole thing. Well, DAT is like all multiple choice anyway, but this is just like how you close it. Well, they might put a multiple choice like of what it would look like in a cyclic form. So this is what you would have to do to make it into the cyclic form right here. The OH on the second carbon is up, same as for the third one, same as for the fourth one. But for the fifth one, you have to be careful here. That's not an alcohol. That's a CH2OH, which will look like that CH2OH right there. Right. When we close the ring, let's just draw in Haworth projection. This. Right. Where this is the anomeric carbon right here, which is our atom number 1, 2, 3, 4, 5, 6. The atom 6 oxygen here is just going to get deprotonated somewhere in the mechanism, making that neutral. And this is our atom number 1 right here, where when we attack that carbonyl carbon and pop this double bond onto the oxygen right there, that will get neutralized by some acid to become alcohol. And I'm drawing a squiggly line here to show that this alcohol can go up or down, right? But we know at carbon 2, the alcohol is going to go up, carbon 3, up, carbon 4, up, carbon 5, the CH2OH is up. But at carbon 1, we have two different anomers, alpha anomer and beta anomer, depending on where the alcohol goes. It could go up or down, right? Now, at this anomer carbon right here, right, we see that there is an OH and an OR group. This is the OR group right there, right? This functional group right here, do you know, do you remember what this functional group is when we have an alcohol and an OR attached to the same carbon? Where half of it is an alcohol, the other half, hemiacetal.
Yes.
Right. What would the acetal look like? Right. Not a hemiacetal, but a full acetal.
Either two OH groups or two OR groups. I forgot.
Yeah, it's gonna be two OR groups right there.
Okay.
Two OH groups, that's something else. That's called a hydrate or a geminal diol. Right? Hydrate or geminal diol, which is very unstable, not isolatable. When you have two OR groups on the same carbon as an acetal, a hemiacetal is half OR, half OH, hemiacetal, which
Wait,
is
what's
this
a ketal?
acetal.
Hemiketal and ketal? What do they look like?
Yeah, a ketal. I think that is just an acetal, but let me make sure what a ketal is actually. Let's see. Yeah, a ketal is just an acetal. Same thing as an acetal. Yeah, another way of saying acetal, ketal.
And how can you tell the difference between alpha and beta again? Was beta the one that's the same as the so carbon 5, that one goes up, and then carbon 1 that could go up or down. What's alpha and beta again? I forgot.
Yeah, so if the OH is cis to the one that's going up on 5, then that's beta, right?
Okay,
If,
beta are the same. Okay.
yeah, CH to OH and anomeric CH to OH and anomeric OH, cis, beta. If they're trans, alpha.
Okay. And on the first structure you drew the line, that one vertical line, and then the one with the anomeric on the left one?
Yeah, this one right here.
No, the left, the very left.
The very left, this one. This
So
anomeric
I
carbon.
forgot. Vertical is what? Wedge or dash? And then horizontal is what? Wedge or dash?
Yeah, so vertical is dash, horizontal is wedge. It's like a
Vertical
person reaching
dash.
out
Okay.
its arms for a hug, like the fishing projection.
Wait, horizontal wedge. Okay, bow tie. Okay, yeah.
Yeah, bow tie. Right. It's like a person reaching out for a hug. Like these are the arms of the person here. So it's reaching out towards you. That's a wedge.
Okay. Wait, okay. Hold up. Let's see. Apparently, hemiacetal and hemiketal are different.
Hemiacetal and hemiketal. Wait, what is the hemiketal? I never heard of that before.
This.
Let's see. Hemiketal. Ketal, hemiacetal.
Oh, okay. So acetal, there's an H group.
I see. So a way you can think about this is that this is a hemiacetal. This is a hemiketal, right? The hemi part will show that
One OH, one OR.
yeah, we have one OH, one OR, the acetal part, think of that as aldehyde.
Oh yeah, that's what I was thinking.
Yeah.
Ketone.
Ketal, ketone. Right? Ketone, 2 R groups, aldehyde, 1 R, 1 H, like that, for the difference between these two.
So because this one started with an aldehyde, it's going to be acetal.
Mm-hmm.
But if it was a ketone, then it's going to be ketone. Okay.
Yeah, right. If it was a ketose, like a CH2OH on the top like this, and then carbonyl right there, and then whatever, and CH2OH like that. If this was a ketose and then it attacked like that, a hemiketal would form. If this was your starting material and this gets attacked right here instead. Right? If this was your starting material, then a hemiketal would form. Okay, which retinal glucose would result in the direct addition of new substituent in the meta position. Okay. So this is talking about benzene EAS reactions, where what is a meta director and what is an orthopara director? Like what kind of group? Electron donating group or electron withdrawing group?
Wait, let me think. Okay, so carbonyls do meta
Yeah, because carbonyls are electron
withdrawing.
groups. Right.
Okay, so withdrawing does meta, and then with the exceptions of halides,
Because halides are electron
donating
withdrawing.
to orthopara.
Yeah, right. And how can you tell if something is an electron withdrawing group and an electron donating group looking at the group on the benzene ring? What is the first thing you look at to determine if it's a EDG or EWG?
The first atom connected to the ring.
The very
So
first
if
atom.
it has a lone pair, then it's electron donating.
Right. Which is this oxygen, this nitrogen, electron donating. Electron donating. This chlorine, electron donating. This is a carbon, the very first atom attached to the benzene ring, not this nitrogen. This is a carbon right here, right?
So
But
electron donating.
which one is electron donating? This one or this one? Think about the partial charges here. Like, do EDGs have a partial negative charge, or partial positive charge? And do EWGs have a partial negative charge or partial positive charge?
Because nitrogen is partial negative, so that makes a carbon attached to, or that nitrile carbon partial positive.
And if it's partial positive, is that an EDG or EWG? Does it want to gain electrons?
EWG.
EWG. So that's our meta director here. This is just an R group with nothing on it, and all R groups are EDGs inductively. So that's the answer right there. Everything else are orthopara directors. This is an meta director, right? Well, the halogen part is a exception because halogen is actually an EWG inductively, but it's still an orthopara director. So that's the exception, right?
Okay,
because
so meta is electron withdrawing.
Yeah, electron withdrawing groups are meta directors. Exception are the halogens. Orthopara directors are all EDGs. Halogens are EWGs because they are very electronegative. They withdraw electrons a lot, but they are orthopara directors because they have pairs of electrons to donate into the ring, making them orthopara directors because when we do resonance here, there's going to be negative charges, ortho and para, to that halogen right there. Right, but this is still considered EWG because that halogen is very electronegative, withdrawing electrons from the ring overall. the tolerance test would be effective for identifying the presence of which of the following compounds. So tolerance test will be a test for aldehydes. So they give you condensed formulas as the answer choices. What do aldehydes look like in condensed formulas? Like what do they show up as in condensed formulas for aldehydes?
CHO.
Yeah, CHO. So you just have to choose the one that has a CHO in it. CHO.
And ketone is COC.
Yeah. Ketone. COC something 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 something, and then aldehyde is CHO at the very end. That's always at the terminal end because aldehyde is always at the terminal end of the structure. Ketones can be somewhere in the middle of the structure. We don't know unless we have the whole condensed formula. Yeah. So this one, okay. This one here. We have CH3, CH2, CH2, OH, CrO3, H2SO4. Okay, so what would this look like in bond line formula?
1, 2, 3. 3 linear carbon chain.
Yeah.
And then an oxygen attached to it, yeah.
An oxygen with
the H.
Yeah. Uh-huh. And what is this functional group here, and what kind is it? Like primary, secondary, tertiary?
Primary alcohol.
Yeah, primary alcohol. And what is this reagent here? Chromium, oxygen, and H2SO4. What kind of agent?
Jones.
Jones reagent, right? And is that an oxidizing reagent, reducing reagent, base, acid, nucleophile, electrophile, solvent?
Oxidizing.
Oxidizing agent, right? So when and what kind of oxidizing agent is it? Is it strong or weak oxidizing agent?
Strong.
Strong oxidizing agent, right? When we react a strong oxidizing agent with primary alcohol, what functional group would we get?
Carboxylic acid.
Yep, carboxylic acid, like this, right? Which the condensed formula of this would look like CH3, which is a CH3, CH2,
COOH.
COOH, right? The COOH is the carboxylic acid part. Yeah. Oh, wait. Were you paying attention yesterday, Joseph, when we went over this ozonosis question with the word
I just pulled up
representation?
the first one. I didn't know it was from the first one.
Oh, I see, I see. But did you like watch that part? Like, or were you like paying attention at that part yesterday,
Yeah,
or were
yeah.
you?
I
Okay,
got
okay.
it.
So yeah, we got that one. Okay, okay. Okay. What is the hybridization state of nitrogen in CH3 to CH2 NH2? So how would you draw this in bond line formula here? What bond line structure here?
So it's gonna be draw one carbon with, yeah, draw one carbon in the center right there, and then have a CH, a methyl going up, and then a methyl going to the left, and then one more to the right,
Uh-huh.
and then to the right, the carbon on the right, you draw an amine, so N, and then H2.
Uh-huh. Is that, yeah, that's it. NH2. this amine right here, and it's asking for the hybridization of this amine right here. So I'm just going to draw out the amine out like this. H, one lone pair of electrons. How many bonding groups are on this nitrogen here? Like how many single bonds and a lone pair are there in total?
4.
4. And if there's 4 bonding groups, what would that be? sp3, sp2,
sp3.
Yeah, sp3. Right. This nitrogen is sp3. They could make this more difficult by asking this here. Like let's say I give you this question. What is the hybridization of the nitrogen on the structure here? How would you draw the bond line structure here? And then we'll go from there.
That's an amide.
Amide, yeah. Same exact thing as this. But we have an amide right here, where this nitrogen right here still has 4 bonding groups attached to it, right? But what's the difference between this and this right here? This nitrogen and this nitrogen here.
Could do resonance.
Yeah. And if we could do resonance, right?
The sp2.
Yeah, sp2. Because it would prefer to be in an sp2 orbital for resonance, right? Where we see this resonance structure here, the nitrogen has 3 bonding groups attached to it. 1 double bond, 1 single bond, and another single bond there. That's 3 total. No pairs of electrons, sp2. And it prefers to be sp2 over sp3 to allow for resonance. IUPAC name. Okay, which are the following products of the reaction? Okay, alkene reaction. Okay, let's see, they have okay. We have an alkene with an HX here. Think of the alkene as a very strong base, strong nucleophile here, right? Where in this case, it's going to act as the base, and this is going to be the acid here. Which one of the carbons do you think is going to get protonated? Would it be this carbon here or this carbon here that's going to get protonated?
The one on the right.
Yeah, the one on the right, because we want the one on the left to have the carbocation, and that's because it's more stable, more substituted. And to have that have the carbocation, we have to make that lose a bond, making this one on the right be the one that grabs the H from HBr, kicks up the Br, and have that carbocation right there, right? And then once we have this carbocation here, what do we always have to look out for? What kind of step do we always have to look out for whenever we have a carbocation?
Hydride or methyl shift?
Yeah, hydride or methyl shift. And can we do any hydride or methyl shifts here at this point?
Yes, you can do a methyl shift.
Yeah, a methyl shift on this left side here, where that methyl group can shift right there to create a tertiary carbocation, which is more stable. But that methyl group that moved is this methyl group right here. After that shift, the Br minus that left will come back and attack the carbocation to give you your final answer here. That, right? It's not going to be this, right? A lot of students would have chose this as the answer because they forget about that methyl shift right there. Oh, wait, why did I circle that? No, this one here. This is the right one here. Wait, not this. Wait. Okay. Aromaticity. Okay. Sorry that. Okay. So for something to be aromatic or anti-aromatic, it has to fulfill these three conditions here. Right? It has to be cyclic. It has to be planar. It has to be fully conjugated. Right? It has to fulfill all of these three requirements to be either aromatic or anti-aromatic. It's going to be aromatic. Oh, shoot. Aromatic if it has an odd pair of electrons. It's going to be anti-aromatic if it has an even pair of electrons. And then it's non-aromatic if it does not fulfill at least one of these conditions here. So does not fulfill one or more conditions. Okay, now let's draw out the answer choices and see which it is. So we got 5 answer choices. That one. We got this one. We got this one. We got this one. And we got this one. Okay, identify the aromaticity, anti-aromaticity, or non-aromaticity of these structures here, one by one.
Anti-aromatic for 1, non-aromatic for
yeah,
2,
nice.
because sp3 for the top carbon.
sp3 roadblock, making that non-aromatic.
And non-aromatic again for the third. Because it's not conjugated.
Yep, not conjugated. sp3, sp2, sp3 roadblocks, not conjugated.
Aromatic for the next one.
Yep. And why doesn't this lone pair of electrons count in the resonance here?
Because if it's added into the pi system, then it's not going to follow n plus or Huckel's rule.
Right. So if it did count, right, that would be an even pair, anti-aromatic, right? But the reason why is because notice how the atom that the pair of electrons it's on, it's already double bonded with that carbon right there. Like this nitrogen here is already double bonded with that carbon, making that p orbital already occupied. So that's why this pair of electrons here is not on the p orbital, it's on an sp2 orbital, right? Because if we look at this structure here, this pair of electrons here will count into the thing, because notice how this nitrogen right here is not double bonded at all. Like it's not double bonded to that carbon, not double bonded to that carbon. If it's not double bonded, then that pair of electrons can do resonance with the ring, and then it will count, right? But this pair of electrons right here will not count because that nitrogen right there is already double bonded with the carbon there. Right? Does that make sense?
Yeah, and then anti for the last one.
Yeah. Right. Let's see. This is gonna be arrow. Well, the last one is a little iffy one. It's either anti or non, because this is the 8-membered ring right here, which it's actually gonna be non-planar because it looks like a boat like that. So that's one of the weird like examples that's non-aromatic, actually, because it's not planar. Right?
Oh, okay.
The other exception that is not planar and non-aromatic is this right here. Right. this 1, 2, 3, 4, 5, even though it has an odd pair of electrons and it's like cyclic, it looks like it's going to be aromatic because it's also fully conjugated, right? But it's not planar. It's not planar because of steric regions here, making that hydrogen go up and this hydrogen go down, and it's gonna like tilt itself. So it's not planar. So that's a not planar structure, and this is also a not planar structure here. Yeah, that's the same thing. Yeah, so that's the answer here, this aromatic pyridine.
Sorry, what do you mean by that even pair of electron or odd pair of electron?
Yeah, so what I mean is how many pairs of electrons are doing resonance in the ring, where we see this structure here. This structure is all cyclic, it's in a ring. This structure is planar. This structure is fully conjugated because all of the atoms in the ring are sp2, 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 sp2. And now we have to see how many pairs of electrons are doing resonance with each other. Right? We see that this pair of electrons can do resonance, that pair of electrons can do resonance like that. Right? That's 2 pairs of electrons that are doing resonance with each other. 2 is an even pair, even number. So this is anti-aromatic.
Oh, okay.
Right. Yeah. Something like this, like let's say a benzene ring. How many pairs of electrons are in that benzene ring that can do resonance?
Oh, 3.
Yeah. And is that an odd pair or even pair?
That's odd.
Odd pair, right? Which makes it aromatic.
Oh.
Yeah. Just like this pyridine here, right? But the pyridine is a trickier example because it has that pair of electrons right there, but that pair of electrons does not count because it's not resonating. It's not participating in the resonance ring. It's only these 3 electrons here, 3 pairs of electrons there, right? Which is why this is aromatic. This pair of electrons here is not resonating. Right? Does that make sense so far?
Yeah, and also like positive charge on the structure doesn't count as anything, right?
Yeah, the positive charge on the structure does not count as a pair of electrons, but a pair of electrons with a negative charge will count, right? So let's say we have this example right here. That's a good point. Because let's say we have something like this compared to this. Okay, I want you to identify each of these structures, if it's aromatic, non-aromatic, or anti-aromatic.
I know the middle one is aromatic because you can count in the negative charge.
And why does this pair of electrons count, but the last one did not count? Like this one, this pair of electrons here did not count in the resonance, but this one does count.
Because it already have like a double bond over there, so can't really go in anymore.
Yeah, right. Whereas this one has no double bond here, no double bond there, so it can count. Aromatic because there's 3.
And the third one is non-aromatic because there's an sp3.
Yeah, sp3 roadblock. This makes it not fully conjugated. It's only partially conjugated because it can only partially do resonance with these 4 atoms here, but it can't do resonance with that carbon right there. It's not fully conjugated.
And for the first one, I think it's aromatic. Is it?
Right. So for the first one here, how many pairs of electrons are doing resonance for this first one here?
2.
2. Right. Is that an odd pair or even pair?
So it's anti-aromatic.
Yeah, anti-aromatic. That's a little tricky to remember because you know how when you think of even, you think that's a nice number. You think aromatic because aromatic is more stable. It's like the opposite. If it's even pair, it's actually anti-aromatic.
And also having the positive sign over there kind of like taking away the invisible hydrogens that making it sp3.
Yeah, it takes away the invisible hydrogen right there. Right, and this is sp2 right here. Yeah.
Oh, okay. Thank you.
Yeah, because it only has 1 hydrogen now, not 2.
Oh, okay. Thank you.
Yeah. where which one of these is the most stable? Let's rank them in order of stability here. Where one is going to be the most.
Aromatic is.
Yeah, aromatic is the most stable, right?
Yeah.
Aromatic, most stable.
Then anti, then non.
So that's a tricky one. Non is actually more stable than anti. Anti is the least stable here. Because of something with anti-orbitals not like aligning like molecular orbital theory. But aromatic is the most stable, then non-aromatic, then anti is the least stable. Like that. Like even though
what was the reason again?
oh, the reason why aromatic is the most stable.
Why is non is higher than anti?
Yeah, non is higher than anti because this is more into molecular orbital theory, which is what I'm not too familiar with in OChem. It has to do something with anti-orbitals, non-bonding
Oh my God,
orbitals.
is that thing that
Like the
I
weird tree branch thing.
yeah, I saw that in PChem and oh my God, I
Yeah.
never
That's more for PChem, not OChem. This is like all you need to know. Like I'm not too sure why the reason non is more stable than anti. I just know it is, but that's more of a PChem reasoning thing.
Oh, for me, I don't even try to learn the PChem stuff. I just skip it and try to get the other stuff right.
Oh my
oh,
god.
that kind of reminds me of that one question that I also got asked where like they were asking for sigma bond and then for pi bond and I think which one is more stable or something or like which one has higher ranking because one is overlapping in certain way. I
Oh
don't know you talk. I don't know.
yeah, like the pi bond, like a double bond, single bond, versus a triple bond, like that.
Yeah, and then they asking like something about overlapping between like sigma
Mhm.
bond comparing to pi bond, which one is more higher
Yeah.
energy? And then,
So, which one of these is the strongest bond?
I know that triple bond has
Mhm.
the strongest, but then it's always my reasoning is that because it has more bonds to kind of break,
Yeah,
right?
that's the reasoning. It has more bonds where um one of the bonds is with an sp orbital overlapping, sp orbital overlap. The other bond is a p orbital overlap, and then the other one is another p orbital overlap, like that. Where the p orbitals have to be parallel. The first p orbital is parallel like this vertically. The other p orbital is horizontal overlap. The other bond is just an sp orbital overlap right there. When alkene, it only has one p orbital overlap and one sp2 orbital overlap. Whereas a single bond has no p orbital overlap and just sp3 p orbital overlap. Right. So a single bond has sp3 overlapping with another sp3. A double bond has an sp2 overlapping with another sp2 and p orbital overlap, whereas a triple bond has an sp orbital overlapping with another sp orbital and two p orbital overlaps, like that. Right? That's a single bond where that's only one bond. This is a double bond where one of the bonds is between sp2, sp2. The other bond is between a p orbital and a p orbital. The triple bond, three bonds are coming from an sp orbital overlapping with another sp orbital and two p orbitals overlapping parallel to each other. Right? Does that make sense so far?
Yeah.
Yeah. Yeah, but this non-aromatic, anti-aromatic stuff is more PChem, like with the anti-bonding orbitals, molecular orbitals, stuff like that.
Okay.
Okay. Yeah. So this one here is going to be retrosynthetic analysis of Poisson condensation. So do you guys remember in our very first session that we did, we talked about Claisen condensation, aldol condensation, those reactions with the what type of nucleophile is used, what type of electrophile is used. Claisen condensation. Okay, so for Claisen condensation, what is our nucleophile?
Wait, what does glycine involve again? Was it like ester or something?
Yeah, ester and enolate.
Okay. Enolate from another ester?
Yeah, the alpha carbon of an ester or a ketone. It doesn't matter for the nucleophile, but for the electrophile, it has to be a carbonyl of an ester. That's the requirement. Carbonyl of an ester. Right? But the nucleophile, it could be an enolate of another ester or a ketone. Most likely another ester though, but it can work with ketone as well. And the product for Claisen, do you guys remember what product it would give you? Like what kind of functional group will it give you?
Was it? There was like
I'm
a
pulling up my
carbonyl, but
notes
then there
again.
was also like an alcohol, right?
Oh,
I
that's for
remember.
aldol, right? A carbonyl alcohol, and then we dehydrate that to the alkene to make the enone. But for this one, it's different. What does Stephanie remember?
Something with double bond.
Double bond. Double bond with carbon and carbon, or double bond with carbon and oxygen?
Anhydride?
Carbon with oxygen. No, carbon with carbons. I think it was 1, 2. Oh my god.
Yeah, so it's gonna be two carbonyls, a dicarbonyl that is a 1,3 relationship with each other. So a 1,3 dicarbonyl. Right. Where it's gonna be something like this right here.
Oh yeah, okay, yeah.
Were you thinking about this right here?
So anhydride?
Not
Yeah.
anhydride, because anhydride would look like this, where there's an oxygen in the middle.
Okay.
Yeah. This is a 1,3 dicarbonyl. 1, 2, 3. There's no oxygen in the middle there. This is 1,3 dicarbonyl. Right. The question here is asking for what is the missing reagent on the second step right here, right? We have this ester right here and a 1,3 dicarbonyl right here. 1, 2, 3. And you know, for Claisen condensation, when the electrophile is the ester, the leaving group of the ester leaves, like the OR group of the ester leaves. In this product here, right, that OR group of this structure right here stays the same. And if that's the case, right, would this be the nucleophile or would this be the electrophile? Like this whole part here. Nucleophile, right? Where the nucleophile is this alpha carbon right here, which is going to be this alpha carbon right here. And that
Wait,
makes
can you repeat the other thing you said about like how the OR group leaves or something?
Yeah. So the electrophile of the Claisen condensation is the ester, right? Like the carbonyl carbon of the ester. For the reaction, the OR group leaves. It always leaves. Right? In the Claisen condensation. But you notice how like this part right here of the reactant is this part right here of the product.
Yeah.
You notice how the OR group did not leave, it stayed.
Yeah.
If it did not leave, then we know that it's not the electrophile. Does that make sense so far?
Yeah.
Yeah, since we know it's not the electrophile, we know it's the nucleophile right here, where the nucleophile is the alpha carbon right there. That gets deprotonated by the base to become the enolate, right? where this nucleophilic alpha carbon here is this nucleophilic alpha carbon right here. What does that make this carbon right here?
Electrophile.
Electrophile, right? So that's the star carbon, the nucleophile. This is the dot carbon, the electrophile. When we try to go backwards and try to see what made this right here, we have to make that cut between the star and dot right there, right? And when we go backwards, this is the original molecule we have right here. This dot carbon right there is the electrophile, which we said is an ester. And the OR group of the ester has to be the exact same OR group of the base we used right there. Right, which this is the OR group right here. This OR group in the mechanism leaves. Right, this is the star nucleophile. This is the dot electrophile right here. This is the leaving group of the ester electrophile leaving group, and it leaves. Does that make sense so far?
Yeah.
Right. Yeah. So we went over something like this in our first session, but I didn't know that DAT actually like tested like going backwards as well. So it's a good thing we went over that. Yeah. That's good. Okay. Is the most acidic. So there's a lot of factors. Do you are you familiar with that question, or do you want to move on to the next one with the Careo acronym, the most acidic question?
I think. Well, S is a bigger atom than oxygen, so it could store more electrons.
Yeah, it can
Or
store more
something like
electrons.
that.
Yeah, S is larger, more polarizable atom, store more electrons, more stable than oxygen. But what's the difference between C and E?
C and E. There's two fluorines in E, so the induction effect is stronger in E.
Yeah, that's right. That's basically it.
Okay.
Yeah. Okay. How many 13C NMR questions would you expect for the following molecule? Okay. So the molecule they gave us is this benzene ring, OH, OCH3, 13C NMR. So the number of peaks we have on this 13C NMR would be the number of unique carbons we have in the structure.
One, two, three, four, five, 6, 7. Oh wait, 1, 2, 3, 4, 5, 6. Oh yeah, okay.
Right. We have 1, 2, 3, 4, 5, 6, and there's a sneaky carbon somewhere. 7, right there. The carbon on that group right there. So 7 unique peaks. What if I have something like this though? How many unique peaks would we have on the 13C NMR here?
1, 2, 3, 4.
Yeah, nice. It's 4 because what's the reason why we have 4 here? Like, what is the difference here?
Symmetry.
Yeah, planar symmetry down that middle, making this 1. These carbons here are considered 2 because they're the exact same chemical environment. This is 3, same exact chemical environment. This is 4. Nice. It's not 1, 2, 3, 4, 5, 6 because of the planar symmetry here.
Okay. Okay, this is not a question that's related to whatever we have here, but so going back to EAS, we have Friedel-Crafts, I think alkylation or something like that. There was like a reaction, I forgot what it was, but it was like something on the benzene. If there's something on the benzene, then you can't do like Friedel-Crafts alkylation or something like that.
Yeah. If the benzene is deactivated, then Friedel-Crafts reactions cannot happen. And what does it mean for a benzene ring to be deactivated? what kind of groups are attached to the benzene ring? EDGs or EWGs? What's a G activator?
EDGs.
So EDGs, what do they do to the benzene ring? Do they donate electrons or withdraw electrons?
Donate.
Donate electrons, right? And if we donate electrons, does that make the benzene a stronger nucleophile or a weaker nucleophile?
Weaker.
Do not work with butyl Crab's reactions. Right. So what is a nucleophile? What charge does a nucleophile have? Negative charge or positive charge?
Negative.
Negative charge, right? So if EDG is donating electrons into the benzene ring and making the benzene ring more negative, the EDG is an activator.
Stronger. Oh, okay.
It makes the benzene a stronger nucleophile, right? Because it's donating electrons, making the benzene more negative, a stronger electrophile, an activator, right? But what is an EWG? What does an EWG do to the ring?
Withdraws electrons from the pi system.
Yeah, withdraws electrons from the pi system. And does that make the pi system more positive charge or more negative charge? If it's
More positive.
more positive charge. And is this a stronger nucleophile or weaker nucleophile? If it's more positive.
It's weaker.
Yeah, weaker nucleophile, which makes an EWG a deactivator. So if there are EWGs on the ring only, then Friedel-Crafts reactions will not happen.
So that means that if it's a strong acid, then it's a deactivator. Because I know that electron withdrawing group kind of making the group like kind of making the whole structure more stable, making the conjugated base more stable and then stronger acid. And I thought it was gonna be stronger in this case too.
Oh, I think you're thinking about
I think I get mixed up things.
yeah, you're thinking about this type of question right here, where they give you a benzene ring with a carboxylic acid. Let's compare this one with this one, and let's say we have an O2, OCH3, and they ask you to circle the one that is more acidic, right? So which one would be more acidic, the left one or the right one?
NO2 is electron wait, there's a plus on the nitrogen, so that means it's electron withdrawing. So that means it withdraws electrons from the
right.
So
it withdraws
that
electrons.
so that means the left one's more acidic.
Right, more acidic because when we draw out the conjugate base of this, right, by deprotonating it and giving that a negative charge, we will have positive charges on the ortho and para positions. I meant to draw it in a different order, but in this case, it doesn't matter because this is an EDG, the OCH3, which puts negative charges on the ortho and para positions. And when we draw out the conjugate base with that negative charge right there, this negative charge right here is more stable than this negative charge because this negative charge right here is closer to positive charges right here, right? Whereas this negative charges here is like close to negative charges. They repel each other. But what if I have something like this right here? Now, which one would be more acidic, this one or this one?
The second.
This one, yeah, because this is also an EWG, which puts positive charges on the ortho and para positions relative to it. When we draw out the conjugate base of this negative charge right here is more stable than this negative charge because you notice how the opposite charges are closer to each other like that. That's why this more stable conjugate base comes with a stronger acid. This one is more acidic than this one right here. Does that make sense so far?
Yeah.
Yeah, so that's different than this concept here, The Friedel-Crafts reaction is yeah, not talking about acidity. Friedel-Crafts reaction is EAS reaction. Does that make
Okay,
sense?
so if there's an EWG on a benzene, so that means you can't do any of the Friedel-Crafts reaction.
Yeah, you can do Friedel-Crafts alkylation, you can do Friedel-Crafts acylation. But if you have an EWG and an EDG on it, Friedel-Crafts reactions can happen. Right? Because this EDG right here, think of it as canceling out the deactivated power of the EWG. Right? So if there's an EDG on there, then Friedel-Crafts reaction can happen. But if it's just an EWG, like there's no EDG there, no reaction would happen here.
So what if it's like a halogen, like a weak?
Oh, if it's a halogen, then no reaction as well. Right? Because if we have, like, let's say bromine NO2, now we have two EWGs, EWG, EWG. Both of these are EWGs, no reaction. They deactivate the ring. There's no EDGs here.
Okay. So what if it's like one EDG and one WG, but then the one with the EWG is stronger than the EDG, like on the ranking?
Yeah, so that's the case for this example here. Like before, when I taught like OChem, like I always thought that this would not work with Friedel-Crafts reaction because this is a stronger EWG than this weak EDG right here. This is an R group, but I've seen some example problems where they can do Friedel-Crafts with this right here.
Oh.
Yeah, it looks weird because you know how this is a strong EWG, this is a weak EDG. So the EWG should take like priority over the EDG, but this EDG here will actually like make Friedel-Crafts reaction happen.
Okay.
But if it's just EWGs, no EDGs at all, Friedel-Crafts reaction would not happen.
Wait, what does acylation do? So alkylation adds more carbons, right? But acylation is what?
Yeah, so alkylation and acylation, they have the same limitation. They do not work on deactivated rings, right? That's the only limitation for acylation. There are two more limitations for alkylation that acylation does not have. Right? So let's go over alkylation first. So let's say we have this benzene ring, and then we have OCH3 here, and then we try to do this Friedel-Crafts alkylation here. The other limitation is carbocation rearrangement. Think of this good leaving group here, leaving by itself to form like that carbocation, and then that carbocation can do a hydride shift to get this more stable carbocation right there. Once that happens, this is the electrophile here. This is the nucleophile, where that electrophile there is bonded to three methyl groups, 1, 2, 3, which is that three methyl group right here, 1, 2, 3. The reason why I put it para to this group right here is because this is an ortho para director, an EDG. But because we activated the ring, we will keep over alkylating. It keeps going on and on and on, right? So those are the two other limitations that it has. Carbocation rearrangement and over alkylation. Right? Whereas in acylation, let's say we have this OCH3, and then we have this acyl group, AlCl3. Right? Now, this, I'm just going to put in the para position to get the major product. You're just substituting the chlorine with the benzene ring here. The carbonyl is still there. The R group is still there, like that. And it only reacts once, right? And there's no carbocation rearrangement here to worry about because no carbocation is going to be formed in the mechanism. It's just going to be as it is right here, where you're just going to substitute this chlorine ring with the benzene ring wherever it is going to react with. Since this is an EDG, it's an ortho para director, I added it to the para position to get the major product there. And the reason why it stops once is because what is this group right here? Is this an EDG or an EWG?
EWG.
Yeah, an EWG, right? And if it's an EWG, is that an activator or a deactivator?
Deactivator.
Yeah, deactivator. So it would deactivate the ring, stopping the reaction from happening again. But what is this R group here? Is this R group an EDG or an EWG?
EDG.
Yeah, EDG, which is an activator. And if it's an activator, it would make the reaction happen again and again and again. That's why it's over alkylates. Right?
Wait, so the one with the EWG,
Mhm.
but the OCH3 is a E. Yeah, that one. OCH3, that one is electron donating.
Mhm.
So it's an activator.
An activator because it donates electrons, making it more negative activator.
Yeah.
Uh-huh.
So it could do it 3 times? Because two ortho position or no?
It can only do it once, but it could add it on 3 positions, either this position, that position, or this position here. I added it to the major position because of less steric hindrance. And then once we add it there, I stopped there. Right?
Okay.
These are just the positions because we know EDGs are ortho para directors, which I just circled the ortho para positions there to show where the group can go. These positions here will be the minor products because of steric hindrance. This position down here is the major product because of less steric hindrance there.
So acylation is adding a carbonyl, and then alkylation is just adding carbons.
Yeah, adding carbons, where those carbons are susceptible to hydride shift or methyl shifts. Because if you want to add this group right here, you will not get that group. You will get the group that is there after rearrangement. Right? Where acylation and alkylation, they have the same limitation of not working on a deactivated ring, but alkylation has 2 more limitations that acylation does not have. Alkylation is susceptible to hydride or methyl shifts, and they could over alkylate. Acylation does not have these 2 limitations here.
So limitation as in like it won't happen or like it's just like something that doesn't happen in the acylation.
Yeah, so limitation as in like why it is not as useful in lab, right?
Oh,
Alkylation, carbocation rearrangement can still happen, but it's undesired. We don't want that. Over alkylation can still happen, which is this one here, but it's undesired. We don't want that.
Wait, so
which
the
is why
carbocation rearrangement, that one only happens on the reagent, like not the actual starting material?
yeah, on the reagent here, not on this actual starting material. It happens on the
Okay.
reagent here, the haloalkane, which is this portion here. This is not the full mechanism. This is just what happens in the mechanism, right? Okay. I'm gonna go get water really quick. I'll be right back.
how's your studying?
Bad. I just started studying bio again today.
My bio score dropped.
To what?
Let me see. I just took it today, my test. I started a little late. 20.
That's still good.
Not really, because if I get 20 on a test day, I'm gonna get 19. And before I got a
No, I had
20.
literally got the same.
You got the same score? I can't get 20 though, because I got 21 on my test.
True. So you need to get 22.
So I need a
I could
22.
get 19 or higher. Because the first time I got 18. And
Yeah.
then second time I got 16.
We're gonna talk about that. Pretend like that one didn't exist. But yeah, yeah, it dropped so much, so that was so bad. Cause the one I took for practice 9, they have like 6 questions about diversity of life, and I hate that section. It's like that. What was that thing? That's like Monera and then Nigdaria. Those things. Oh, taxonomy.
Oh, I
Taxonomy.
hate
Yeah,
that.
yeah. That one I
I
was
just
like,
no, I
go
skipped
go
that.
over.
I don't even try to learn it because there's so many things to remember.
Yeah. So if you don't learn that on the practice test 9, you're gonna score really bad. That's that.
Like I'll review it, but I'm not gonna try to memorize it
Me too.
because there's too many things to remember.
Yeah.
Okay, I'm back. Let's do
No?
1 or 2 more questions and then call it a day.
Okay. Wait, so are we still doing the library thing tomorrow?
Oh, the in-person one.
Yeah.
I'm free tomorrow. Is Joseph?
Maybe in like we could no, let's not do library. Let's do like a cafe or something
Cafe.
Why?
because it closed later.
Cafe close later?
Yeah, at like 7 leaves. They close at like 9 or 10.
The library closed at 9.
Oh, really?
Yeah, Mufreda's library closed at 9.
Oh, I thought they closed at 6.
No, only on Friday.
Do we need to review this? No, we don't.
Which one?
Undergo an E1 reaction the fastest. I think I get this. Yes.
Let me see. I think there's some questions I have for
Oh, do
9.
this one. This
Oh,
is
which
more
one?
of a like a lab.
Hmm. Oh shoot. During an acid-base extraction, aqueous sodium hydroxide is added to a mixture of benzene and compound X and hexanes. Compound X is then isolated from aqueous layer. Okay, so this one here is saying that they are purifying or separating a benzene from compound X, right? Imagine in lab, you have a flask of these together, a benzene and compound X, but you want to separate them and purify them. To do that, they have to have different chemical properties like polar, non-polar, soluble, insoluble, right? Where they were able to separate them out into 2 different flasks, like let's say one flask with all benzenes, and then another flask with just compound X, right? So what is the chemical property of benzene here? Is this non-polar or polar?
Non-polar.
Yep, non-polar. So what does that make the compound X, the unknown compound X? Here, if they are separated, what is the opposite of
Polar.
non-polar? Polar, right? Where let's draw out the things here, the answer choices: C6H5 COOH, C6 H5 C6 H5 CCl4 C6 H5 CH3 C6 H5O CH2 CH3. So the non-polar and polar thing is actually not the best property to look at because the answer choices here has a lot of polar molecules, right? But the question also says that we are reacting this with NaOH, right? So if we are reacting this with NaOH, what property do you guys think can be used to separate them, right?
Compound X.
Compound X and benzene, they're separated, meaning that if they're reacting with NaOH in aqueous solution, one is soluble and one is insoluble. Is benzene soluble or insoluble in aqueous solution?
Insoluble.
Insoluble, right? Which makes compound X
Soluble.
soluble in aqueous solution. Which one of these answer choices here are soluble in aqueous solution here?
The first one, because the carboxylic acid.
Yeah, the first one, because of the carboxylic acid here, where that carboxylic acid can get deprotonated and there's an H bond right there.
Also the last one, right? Or no?
This last one here is an ether. Right. This one here is not soluble in water. The ether is insoluble.
Wait,
There's no
why?
H bond.
Oh, but isn't it polar?
Yeah, it is polar, which is why this is not the best property to look at, because this is also polar, but it is not soluble.
Oh,
It's insoluble.
okay.
Which is why it's not compound X, because compound X is soluble. This is insoluble. Because it has no H bond. H bond is any compound that has H bonded to one of these three atoms, F, O, or N. Fluorine, oxygen, or nitrogen, where we see this hydrogen here is bonded to the oxygen right there. But this oxygen right here is bonded to a carbon and a carbon, not a hydrogen. So no H bonds, not soluble. But it is polar though, because oxygen is partial negative, carbon is partial positive, but no H bonds, not soluble, insoluble. This is polar, but insoluble in water, aqueous solution. This is polar and soluble, which matches up with the properties of compound X right here. Okay.
I think this one.
Okay, this one. Okay. Yeah, let's go with this one. What time are we going to meet tomorrow at the library?
I think Joseph, I think he's very busy with all of the Zoom meetings.
Well, tomorrow's in-person meeting and it ends at 1, but I
Oh,
think
but
they are treating us out for lunch. So maybe like, let's say 3. And Brian, I can pick you up.
Okay, thank you. Okay.
okay. Sorry.
Wait, did Tiffany say something?
So 3, is it confirmed? Just
Yeah,
Yeah,
3.
like around 3 or 3:30, but I think 3.
Yeah.
okay.
Okay, so we have this negative charge here. And what is the partial charge of this carbon right here attached to 2 carbonyls?
Positive.
Partial positive, making that the electrophile. Carbonyl attack electrophile. But what's the problem here when we make that new bond between them? If we make that new bond between them, how many bonds would that
Too
carbon have?
many electrons.
Too many electrons? Great. So what do we have to do to conserve the octet rule?
Push one of the bonds to the oxygen.
Right. And then once we make that happen, we make a new bond between the nucleophile and electrophile. Like that. That's the new bond right there. The carbonyl at the top is still there, but that double bond on the oxygen is no longer there. It's now a single bond. And what charge would that oxygen have as it gains a pair of electrons?
Oh, negative.
Negative charge. That's the answer.
Okay.
Yeah, that's it. Let me